Okay, so what scientists were going to do, what they tried to do was to compare the travel time when the light was traveling along the direction of the Earth's motion through the ether, and compare that travel time as light bounced between mirrors to the direction perpendicular to that motion. So they basically wanted to set up some sort of experiment where they could measure the travel time of light in two different directions and compare the times, and thus deduced the speed of light in those two different directions. And what they supposed was that what they expected is that since light was traveling through the ether, that the light would travel, the speed of light along the direction of the ether would be different than the speed of light perpendicular to the direction of the ether. So the most famous experiment of this kind was done by Michelson and Morley, and again, this experiment was simply designed to determine the speed at which the Earth moved through this hypothetical ether during its orbital motion. So here's a schematic of the original Michelson and Morley experiment. Here, light enters over here. Okay, that's where light comes in. It travels along this direction. This element here, B, is a beam splitter, which basically is a partially reflecting piece of glass. So half the light goes off in this direction and half the light goes off in that direction. And then in these different directions, then light will bounce back and forth, for example, between mirrors E and D in this direction many times, and then between D1 and E1 in this direction many times. And then what's not really shown is that the beams get recombined on this beam splitter again, B, and then now both beams will travel this direction and basically be detected by this telescope over here. Okay, now they've basically, in this schematic, the beams are sort of separated. You can see how each reflection looks like a separate path, but in fact these paths are overlapped, okay, in space. But this is just to show you that they bounce back and forth many times. Now we're going to simplify this so that it's a little bit easier to think about, and then so we can label some things a little bit easier. So I'm going to draw a more simplified, a much more simplified version of this right now that contains all the important elements. Okay, so here's a schematic. Here's a much more simplified schematic. We have two arms of this device, which is actually called an interferometer, analogous to the two perpendicular directions in the original experiment. Each of the arms has a length L, and that L actually is the total travel distance for the light bouncing back and forth many times. That's the total cumulative distance traveled by the light in each of these arms, arm A and arm B. There's a beam splitter here that separates the beams so that one goes up into arm B and comes back down. Again, this represents many back and forth. This represents, many times back and forth as well, and bouncing between the beam splitter and B and the beam splitter and A. Okay. Then the two beams get recombined on the beam splitter and get measured by some sort of detector, which is represented by this eye. Now, something we haven't talked about is what kind of measurement does this device make? Does this instrument make? Well, these are light waves, and so if their distances traveled are slightly different because the velocities are different, then the two waves in the different arms, when they're recombined at the detector, will have slightly different, will be shifted in phase, the two waves, and they'll interfere either destructively or constructively, making fringes.